Oh, Niranjan.
Good morning. Good morning, Dr. Fajes.
Hey. Anything you guys have for me? Any comments? So I have some comments. I graded your homework and I think the index notation is at least more than half of the class is not completely comfortable with. And including the dyadic notation based on your homework again. I tried to be careful and try to mark everything I saw in your homework and go through it. And the exam is going to cover things that you missed. Like I did mark or made a I made a note of what most of you missed, like not in person, but on an average, if I felt that many of you missed. So I will surely ask that question. So the exam will cover things that missed. Few of the things I can tell you, I felt that this is so few of the points you want to review is vector identities, using index notation. Again, I'm not saying to a particular person on average, with some sort of struggle in dyadic notation that trace in dyadic notation. Like that's just an example phrase, but just dyadic notation, it seems like you struggle. So there will be a question on, like remember, there was this question about gradient of P dotted with R over R cube and so on. You were asked to find out what that was. Again, I felt that some of you, it is easy not to use the dyadic notation and do the problem. And that is okay, but in a more complicated scenario, you may not be able to, you may not have the time to do that. Like for example, in an exam, if there are 6 questions, if you try to prove it using the actual notations, it might come out very hard. So you start using this identities and work out everything. It is possible to work out almost every vector identity just based on these two. So I'll give you a problem which is not straightforward, and unless you use this, it may not be straightforward. So that's one thing. Delta functions. I was a little surprised that electromagnetic configuration using delta functions, almost everyone had difficulty with that. So think of a disk in YZ plane. Do them complicated examples like that. Like in the exam, in the homework, it was disk in the XY plane. That is easy because the angle theta in the spherical coordinates gives you that. This makes it a little harder. So try to do that. And connection symbol. Not really the complete connection symbols. Connection symbol is a good place where you learn how to operate vectors and vectors that are position dependent. So that's a practice. So if you notice in the last exam, I asked one particular component out of this, which takes only very less time to do. But if you know, if you don't make them necessary. Again, this is not the 5 questions I'm trying to say. These are the things I felt you made a lot of mistakes on, or you struggle on an average, the class struggle. So make sure you go over this. Again, these are not the questions I'm going to ask them, but probably something related to this is what my plan is. Does that help? Or at least surely go over this for the exam. Okay. There's a homework that was due today. And I noticed that the last part of the homework, I think it will help if I go through it today. So even if you submit it on Monday, I'm good with that. But if you have finished it, some of you probably already know how to work on it. But if you want, you can postpone it to Monday too, because last part of the question, I need to go over it today. So homework 4 is due today, basically, but you can postpone it if you want. And there'll be a homework 5, which I have not posted yet, but I'll post it very soon. I've prepared it, but I want to go over it carefully. Because that's a new question I made, so I want to be careful that that is a mistake. So maybe 1 hour or so after this class period, I'll try to post it. So that's due on the day of that, anytime before the exam. So that's 29. Right, and midterm 1 is on. Now this has this feature that you will not be able to get a feedback on homework 5 because I won't be able to grade it. So what I suggest is that if you really want to get it graded, at least one of you submits it before September 29, and I'll grade it and give it back to you. So give me about half a day and I can grade it and give it back to you. But from the question that I'm making, it is more of a descriptive question. There are 2 types of questions I have. One is where you don't have the answer. One is really you go through all the steps. It's as if you go through a textbook. So this is more in the textbook style question. So hopefully it should not have any, like all the answers are there in the question paper itself. So it's just a matter of what the, how to go from one step to the other. So hopefully it won't hurt you. But if you really want a grading of your homework, do it at least 1 day before, 24 hours before, and give me half a day and I'll grade it and give it back to you. Okay. So that's my comments on the exam that you have in a week. Anything you want to ask?
The homework 5 gonna be in the midterm.
Yes, it is very related to what we have already done. So it's just basically motivating unitary operators in the context of what we did. I think it's very related. Again, if you want to give, these are the important ones. How about? Right. These are the most probably I'll be asking out of this, but surely one question from eigenvalues and eigenvectors, there is a question that I will ask. Those are all very easy to questions, and probably you guys will do good also. But these things, I'm afraid that some of you will struggle, at least based on what I saw on the homework. So, so that's what it's going to be. Okay. Any other questions?
We are doing it in the class, right? In morning.
Yes. Is there any other suggestion? You want to make it earlier? You guys decide. 9:30 to 9:35 to 10:50 is the official time. If as a whole class, there's a consensus that you want to start early, that's an option. If as a whole class, if you want it in the evening, as a whole class, everyone together. If you want it in the evening, that is also perfectly fine. This is Friday. Yeah, anytime I'm okay. How about that? Any other time, I'm okay.
Maybe 9:30 start. 9.
9 o'clock, half an hour early? Yeah, sure. That's that surely. That's the easiest thing to do, and I have done this before, and that works out well. Usually, is everyone available before 9:30? Ask Nathan also. I think he's not coming today. He's not well. At least I read the first line of the. So he also has to agree. By any chance, if he has a class before this, then it doesn't work. Yeah. It's just fun.
Date.
Hmm?
I start at 9:30. I start at 9 and 5. That's something else.
But then he loses half an hour. That's not bad. He will sue you. If not you, he will sue me. That's a very good reason to sue, right? I mean, I didn't get half an hour. Like you would sue, right? If I don't give you half an hour. Yeah. Or at least I mean sue in the sense you will feel it will be very unfair on you, right? If I take away half an hour from you and not. I'm pretty sure he'll be available. So if not, we will find a way. So, like maybe after the class, you have this exam, sorry, this class, so that doesn't work. Yeah, yeah, hopefully it will be, but all these things sometimes extra time does help, right? Because you can make mistakes and you go around in a circular way. There are many, yeah, you can see how time can help, but it has to be uniform. Talk again between you guys, and okay. If you really think time is going to help, evening is also fine. After your E&M class, are you guys available? No. No. Okay. If one person is not available, then we can't have. So yeah.
Yeah,
So-
that's on Monday.
No, before class, surely. I'm saying that'll give you only half an hour if you want more time. Like let's say this is 75-minute class, suppose you want 150 minutes, right? Or 200 minutes, so then you can have a evening. But again, that typically I've noticed that you guys have PA to do. Someone or the other surely has a PA assignment and it doesn't work. Let's keep it simple. Let's make it 9 o'clock. Most probably you'll be there. And some of you guys probably will sleep away and that's your fault. That I think is okay. Okay, that's good enough. Anything else by any chance? No? We broadly, at least in the context of Stern-Gerlach experiment, I tried to, in a very quick way, try to tell you how you can measure something, and then you measure it in another basis, then it suddenly gets disturbed, right? So that's the idea of quantum mechanics, and based on that, you can do a lot of stuff, but we cannot go into the details of quantum mechanics. But again, here the idea is to at least provide you with the mathematical machinery so that whenever you see this in more detail, at least the mathematical machinery doesn't bother you. So one of the common things you have is polymatrices. Let's talk about that and talk about polymatrices comes like, remember there was this a Stern-Gerlach setup, and we had this interaction energy Hamiltonian was equal to some constant, some h naught, let's say. Cannot be h naught, right? So minus mu dotted with b, right? That's for sure. mu is the magnetic moment, and that is Q over 2m times the angular momentum. If the angular momentum is purely spin based, then and especially if it is a spin half, then you would say this is h bar over 2 times the poly matrices. And whenever we say this sigma in here, sigma is a vector. Say that's sigma x in the I hat direction plus sigma y in the j hat direction plus sigma z in the k hat direction. If I were to say the magnetic field is similarly equal to a constant times a direction, so let's say this is sine theta cosine phi, the I hat direction. So this is basically v r hat. So that's some arbitrary direction in space. This is sine theta sine phi j hat direction plus cosine theta in the k hat. That's the in spherical coordinates, that's the unit vector. If that's your description, the interaction energy is minus Q over 2m, so QB over 2m h bar over 2, so let me call that h naught, right? That h naught is equal to QB over 2 times m minus h bar over 2. They collected all the dimensional quantities so that everything else is dimensional. And what is left out is sigma dotted with r hat. And last time I opened this up, so basically you multiply these two out, right? So you can show that sigma dotted with r hat is equal to multiply these quantities, so that sine theta times cosine phi in the sigma x matrix is multiplied by that, then you have sine theta sine phi sigma y direction in a sense, and cosine theta. I haven't yet provided you with what sigma x, sigma y, sigma z is. And now I say that sigma in the basis of sigma z. And this may not be very clear what this means, sigma in the basis of sigma z. I'll tell that in a minute, but to begin with, let me proceed. So sigma x as a matrix representation in this basis, which I haven't, I'm using a notation which I'm going to tell in a few minutes, and that's equal to 0, 1, 1, 0. Sigma y is equal to 0 minus I, 0, and sigma z was 1, 0, 0. Notice that sigma z is diagonal. That's because it's in the basis of sigma z. Whenever I write the matrix in its own basis, then it will come out diagonal. We'll tell that, I'll illustrate that more. But if we use this, and now I multiply these quantities, so when I multiply this, I have to multiply this with sine theta cosine phi, this with sine theta sine phi, and so on. So sigma dotted with hat comes out to be, there is a So the one component is only coming from sigma z, that's cosine theta. The 2-1 component, there is a one x and a y piece is coming in there, but no z component. And that itself is there is a sine theta, which is common in both x and y, and there is cosine phi plus I sine phi. We did this last time too, and here we have sine theta again. We have the sine phi minus I sine phi, and this is minus the sine theta. That's equal to the sine theta. Sine theta e raised to minus I phi. Sine theta e raised to I phi minus sine theta. That's a general description. And now, if I were to call this the matrix, this is a vector dotted with r hat, one sided with a scalar afterwards. This depends only on angle theta and phi. Notice this has a vector sign on it. This doesn't have a vector sign on it, so that's a scalar, but still a matrix. This is a matrix, but a scalar. Here, sigma is a vector, right? So there are 3 components to that sigma vector. And you will notice that if I were to set theta is equal to 0 and phi was equal to 0, this is theta is equal to 0, so that's 1. Sine theta is equal to 0 because theta is equal to 0 means sine theta is 0, so that's 0, 0, and that's minus 1. That's nothing but sigma z. So in a sense, it is picking the z component of the sigma in this case, and theta is equal to 0 and phi. That's just an observation. Do one more, theta is equal to pi by 2 and phi is equal to 0. That's equal to theta equal to pi by 2 makes the diagonal 0. And sine theta equal to pi by 2 makes that 1. And so this is 1 and e raised to here, right? E raised to I phi. So phi is pi by 2, so that's I, right? So that's minus I, and that's I. That's phi is 2. Phi is phi is 0. That's right. Yeah, sorry. Yeah. Yeah, that's the next one, right? So this is 0. Yeah, that's 0 again. So this is 0. That's 0. Sine theta is 1. So phi is 0. So that's 1 and 1. Thank you. Which is nothing but sigma x. And do the same thing once more, and you realize that pi by 2, and then phi is also pi by 2. Right? Phi is pi is to be pi by 2, right? Yeah. That's equal to 0. This is minus I. That's I. That's it. And that's equal to sigma 1. It's interesting. I think in your homework you try to do the eigenvectors for this. Do you do the eigenvectors in the homework? Eigenvectors also, not just yeah, if you see, make an observation there that this angles are half angles. It is when you go from, or it's not necessarily on a sphere. If you do phi going from 0 to 2 pi, you don't come back to the same point. So that's an observation you want to make, and that's a property associated with spin. But again, we won't go It's not necessary to go into the details here in this syntax, somewhere else in quantum mechanics that plays a very nice role. So that's one observation, but as I said, here, this is in the basis of sigma z. So in principle, I could have done this in any basis, and that's what I want to illustrate here. That's basically the eigenbasis dependence. So let's see what we mean by a matrix representation of a matrix itself. So let's say you have sigma z, right? So that is sigma z is there. To begin with, I don't know its eigenvectors. So let me say that its eigenvectors are, so sigma z is a matrix. It could begin with this itself and that way. So, but immediately, yeah, let's start with the simplest way, right? It's nothing wrong in taking an actual representation. So that's one. And what are its eigenvalues? It is and Dirac has this following notation, which is called the bracket notation, but there is also bracket is very common notation. There's also one more notation he introduced that whenever you're thinking of an operator, its eigenvalues will be the prime. So eigenvalues will be marked as sigma z prime. And whenever you see a prime, that means it's an eigenvalue. So sigma z prime here, that's eigenvalues, that's equal to plus or minus 1. Next, we want to say eigenvectors. Again, in Dirac's notation, you would say eigenvectors are, you would say eigenvector associated with the first one. So it's sufficient to write this plus, but we are very quickly going to go in different bases. So if you're going in different bases, I had to specify which basis am I using. So in this case, I'm using the sigma z basis. So this is sigma z prime equal to plus 1. So this is the eigenvector associated, that's a notation now, associated with eigenvalue plus 1 of the matrix sigma z. Notice there is a sufficient amount of notation inbuilt in that. Now, often what happens is that in a context that you're working with, it is not necessary to write so much. So often you will just simplify this to plus 1. That's perfectly fine. As far as you know which basis you're working on, you can simplify it. But in this particular scenario, you will notice that it is necessary to write. And same thing, we have another vector, so that is sigma z prime is equal to minus 1. We have to specify this. Since it is a simple matrix, this comes out to be very simple. So that's equal to 1, 0. I just have to check it. You can, of course, solve for this. If I had to multiply this with this, I will get back the same vector. That is all I have to do with plus 1 as your vector. Same thing, sigma z prime is equal to minus 1. Eigenvector associated with that is 0, 1. Again, check that this multiplied. No, that's wrong. Yeah, that's correct, right? Yeah, this multiplied with this is first row gives you 0, second one gives you minus 1, but that's the minus 1 that is needed for the eigenvalue. So those are the two solutions. But now notice, now I need so this in our notation that we have been using, this is basically E1 if you want, and that's E2. Right, we have two eigenvectors, so now this is E1 and E2. Most of the time we are here, these are complex numbers. Most of spherical coordinates and cylindrical coordinates that we worked with, they were all real. So the associated reciprocal vectors has to be complex conjugated. So you have to make sure that so E1 will be equal to E1 star. So it is a dagger in principle, so you have to change the direction, but for our purposes, it is sufficient to just take a star. So this is, if you just take a star and make it a row vector, that is good enough. And E2 is equal to E2 that. And dagger is transpose plus complex conjugate. Okay, so that's
Your eigenvector for S1
this one.
0, 1 or 1, 0.
Plus 1 is 1. Doesn't it work? 1, 0. Yeah, it gives me back that vector, right? What's the confusion? I didn't understand the confusion.
So it's 0, 1 for S1.
Very simple. So 1, 0, 0 minus 1, right? Multiply with 1, 0 is equal to, that gives me 1, and that's 0, right? So I can write this as plus 1. So eigenvalue is plus 1 and eigenvalue. So yeah. Interesting you asked that because in the homework, somehow I made this minus 1, and that's the reason why I'm waiting. I want to change that to plus 1, so a lot of notation. And it's just came out like that. No notation as such. But this is surely correct, right? If this is true, this one is eigenvector associated with plus 1 because I just checked it. So that's the definition. Okay, so now we have two at least one eigenbasis, simplest matrix, very simple eigenbasis. But now, once I have a matrix, remember, if I have a matrix A, if I have a vector A, if I'm interested in the components of A, what I do is I just multiply by 1, right? In this case, I can do 1 dotted with A. Let me do the other way. So A dotted with 1. And that is equal to A dotted with E E1 plus E2 E2. And this time, yeah, this is remember 1 and 2. The complex conjugation is inbuilt in here. Don't forget that in complex, our matrices will have complex pieces in it. Whenever you evaluate this, you have to complex conjugate that. So if you're not getting the answer, you might have forgotten to do the complex. This is the same as A dotted with E1. I've repeated this sufficient number of times. A dotted with E2 times E2. Identify this as A1 times E1 plus A2 times E2. So notice I'm identifying the components of a vector. So A1 is equal to the vector, if I know the structure of the vector, dotted with E1. A2 components of the vector. Component 1, component 2 of the vector is this. I am here working with matrices, right? I'm not working with vectors. So I want the components of a matrix. So let's say M is my matrix. A matrix has 2 indices. So I do this on both sides. So I multiply by 1 on the left and 1 on the right. Notice the trick I'm doing. And then I say this is, suppose there are 2 of them. So this is E, same idea, E1 plus E2, got it. E1 plus E2. Collect this together and you realize that there are 4 pieces in this. So there is an E1 and then there is a scalar number, this dotted with this M dotted with E1 and then E1 again. That's the first piece. Second piece is E1 dotted with M dotted with E2 times E2. And let me write it here, but the idea is, you notice this is not a matrix. This is, I can in principle write this as a row. I don't have to break this, but that's just for organization, that I'm breaking it into 2 rows and writing it in the right form. But this is not really a matrix at this stage. This is just numbers and vectors in a sense. So this is E2 dotted with 1 plus E2 and E2. This can be written as, let me collect them. If you notice, this can be written as E1, or let me just leave it like, yeah, I know. Just let me write it in the form. E1, E2, then I have M11, M12, M21, M22, and 1, 2. Right. So this is M11 times E1, and then multiply with E1, M11, M12 multiply with E2, and multiply with E1. So that's the 4 pieces. But what are the M11, M12? So this is Mij. These are the components of the matrix. Is equal to EI. I is upstairs. How did that come upstairs? So, hold on. Okay, let me erase something. Okay, just it doesn't really matter in this case, but it is better. Like usually, the second vector should be upstairs, so I can do this either way. This is good to write it like this, just to help you guys in general. So at the cost of a bit of confusion, let me do that. Sorry about that. There is nothing wrong here in principle, but it helps to keep that in front. This is 1, 1. Sorry about that. And then this will be. Oh, this one I did write. But no, here it's again almost. Start with this. Then we don't want to write this. Because this is downstream. So then we would say this is E1, E2. And then like this is E1 down. Again, just a matter of organization that either way it should not work. That's it. Operator, so that comes out as an operator. Okay, Mij here, that's what I got, I was pointing out. So now you have I dotted with M. Dotted with J.
When you multiply those two right together, then M and E.
M and E, this is the outer product. Outer product, so this will give you a matrix. That's an operator, right? So it's structure of the operators. So these are the components of M. So this is what we're interested in. That's your matrix. So let's see what is that matrix, right? Let's have, we are doing a simple matrix, so let's start with sigma z, right? Sigma z as a matrix would be, let's call it something. So these are the components, right? So this will be EI. So this one is sigma z equal to +1. That's the first one, and the other one is also first one. So that's sigma z equals to +1. That's the first component. That's the matrix. That's what it means to write sigma z in the basis of sigma z itself. Do the two eigenvectors. So now notice there is a notation here that +1 is the first eigenvalue, -1 is the second eigenvalue. You can change it as -1 is the first eigenvalue and +1, and that will change the matrix altogether. C equals +1 sigma z. Okay. That's, can I erase this or should I go to the other side? Anyone still writing? Yeah, this one I usually
Yeah, so
is, where is it? Nahida? Okay. Okay, so, but I can evaluate this. I know how sigma z operates on sigma, right? Eigenvalue equation says that sigma z operating on sigma z equal to +1. That's the eigenvector, right? Of sigma z. That means it will be +1 times sigma z equal to +1. The eigenvector means this is the eigenvalue +1. This is the eigenvector. Same thing, sigma z acting on sigma z equal to -1 will be equal to -1 times sigma z equal to -1. That's straightforward, simple definition. Use that now. I can use that here. This is equal to same thing with +1. This is +1, -1, -1. Okay, so this is sigma z equal to +1. Writing in this case, it seems like it is a dummy writing we are doing, but in the next example that we do, it will be very fast. So that's +1 here, so that's +1 in a sense. This one is +1. Sigma z equal to -1 times sigma z +1. -1, so it's -1 times sigma z equal to -1 and -1 again. Hopefully it's all very clear, like please ask me questions because this is what is the machinery that goes, it's not even a machinery. The notation of expectation, what we know about this. Okay. This has a scalar product associated with it. There is a dot product. They are usually orthogonal, almost always they're even if they're not orthogonal, we can make it orthogonal. Eigenvector can always be made orthogonal. That's by construction, you can do that. And in this case, the way it is orthogonal, right? The standard matrix product, this times this is 0. So that's equal to 0. That means this is orthogonal to that. This is 0. This is 1 orthonormal. This is 0. That's 1. So you have +1, 0, 0, -1. So that always comes out that way. Like it will always be like that, that if you write the matrix in its own basis, eigenvalues will stand in the diagonal and everything else will be 0. So the matrix is diagonal with its eigenvalues on the diagonal. That is another way you can write this if you notice, and that is that that is a following actually yeah, I mean we have to go back to that. Oh, erase that. Yeah, let me come back to that. So the matrix M, these are the components of the matrix. The matrix itself had this shape, right? So this was E, yeah, I think I can use E1, yeah, it's clear. So this M 1 1, M 1 2, M 2 1, M 2 2, and the rest this 1 and 2. Sorry. If I have to now write this for sigma z, these are in principle the components, right? I mean, this was ij 1 1 2 2 2 1 2. But the actual matrix itself, if I have to write, I have to bring in all these 4 pieces, right? It has to have that operator form. So write that in here. So this is sigma z equal to +1, sigma z equal to -1, and then you have, now we know this, so this is 1 0 0 -1, and I have sigma z equal to +1, sigma z equal to -1. That's how it is. Do the multiplication. This is the outer product, remember? So this is 1 times this, 0 times the other one. And then I have to multiply 1 times this with this. So the only thing that survives, remember, this is the outer product. Everyone knows the outer product, right? We have all done that outer product, familiar? Right? Quickly say that in case there is any confusion. So A, B, C, B times E times F, the outer product would be equal to A times E, multiplying this. What do you want? A, okay. Is that correct?
4
Yeah, this will be a 4 by 4, right? So this is correct, C now, and B times F, right? C times E.
So it's AE, AF, EE, EF.
Oh, plus, is it?
No, it's other thing.
Help, yeah, I'm confused.
It's AE,
Tell me,
AF,
AF,
and BE after AF. EE, EF.
now, how can it be 4? How can it be
Most
4?
like each element will correspond to make it the second vector.
Huh? Huh? Okay. Hold on. The Mij, right? So this is Mij. And then, I'm confused here. So then, yeah, that is a summation also, right? Yeah, Mij, and then that is Ei, right? Yeah, that's a summation. Yeah. Right. So this is, I, J, 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 right? So this, second, yeah, second, the row multiplied by this, but this is the row and this is the column. This is the row, that's the column, so I have to add, I suppose, AC. So. It's, hold on. AE plus CF. Yeah, AE plus CF. And then BE plus BF. And what else do I do? Help me.
I will put the should be plus.
Hmm?
Dr. Sajesh,
This is it, right? This is the vector. Yeah, Niranjan, help.
answer has to be 1/2 matrix, right? The dimensions of the answer.
1/2, correct. So yeah, maybe that's what I was thinking. It will be a 4 by 4 matrix. Sorry. Yeah, so this is having one piece here and one piece there, right? That's all. So it is it is just AE plus CF. BE plus BF. Is that correct?
I think so.
Yeah, okay, at least one. Are you muted? Huh?
I will put that you have to multiply the second vector of matrix, each one of them.
No, but then that would be, no, that's not what I mean. Okay, how about this? Oh, what I mean is, this piece, right? We usually do the matrix as this times this, correct? Here, we are doing this times that. Right? A times E, C times F. I need that because of this summation, not in J's sum. Like I just sort of follow this. This is a way of remembering it, right? Okay, sorry, I never got stuck here. So outer product, the way I am saying it here is that is a matrix times a vector. This is a row vector. A times E, C times F. This is B times C, D times F. Just a notation. If you one. Okay. Okay. Anything? So hopefully it will all work out. We'll see. Okay, now that I've got confused, I have to now multiply this. Okay, so let's do this properly. So this is sigma z equal to +1, sigma z equal to -1. Keep that as it is. And this one now, this will be a row vector, this times this and 0 times that. Sigma z is equal to +1. Notation, I did not bring this up. This was E1 and another notation here. Is this, are you there? Yeah, okay. Another notation is that this one is equal to the bra, right? Bra we forgot. This is sigma z prime is equal to +1. Oh, I have not been writing the sigma z prime here. It's lazy. Sigma z prime is equal to -2. So that's a bra, that's the cat. That's a notation. So since this is the opposite, I should be careful. Should I be? Sorry. The whole idea was that do it in detail so that there is no confusion. I messed up myself. Okay, sorry about that. Okay, so hopefully we will out. That's equal to +1 and now -1, right? So this is 0, this -1. So this is minus, this is a comma now. Minus of sigma z equal to -2. Notice in Dirac's notation, this all should be prime. We are saying the eigenvector associated with the eigenvalue -1. Eigenvalue is prime, right? But I have been not very nice, so I have been writing the matrix. So Dirac would have wrote prime there, and in your homework you will see the prime there. Prime means if the eigenvalue is equal to plus a matrix equal to +1 doesn't mean much. Okay, so this one works, I suppose. So that's equal to now again this times this plus, right? That is an addition there. So this is plus vector +1, the eigenvalue, times sigma z equal to sigma z prime is equal to +1, and sigma z prime is equal to -1. Right? Notice that the outer product that we write it as E1, right? Whenever we do not write the vector product in -1, so minus of sigma z prime is equal to -1, and sigma z prime is equal to -1. Notice how it is coming if you were to make this observation. There is a first eigenvector of sigma z prime, so it's a sigma z prime, which is +1. That's a first eigenvector times or let me call it lambda1, right? Lambda1 E1 upstairs 1 times downstairs, right? First eigenvector plus lambda2 E2 E2. Always that will happen. If you write the matrix in its own eigenbasis, it is nothing but eigenvalue, eigenvector, eigenvalue, eigenvector. Always. That's kind of the definition of the matrix in a sense. Yeah. Any questions on this? This is the simplest one. Let's do sigma z in the eigenbasis of, sorry, sigma x in the eigenbasis of this. This time I'll go a little quicker. So, this will keep in mind. Let's say yeah. So let's have sigma x. No? Sigma x is 0, 1, 1, 0. And its eigenvalues are again plus or minus 1, and its eigenvector is sigma x equal to plus 1. There we go. Sigma x prime equal to plus 1. Okay. Is equal to. Yes. 1/2 times 1, 1. Okay. 0, 1, 1, 0. 1, 1 is equal to 0, 1, 1. So that's correct, and that's a plus 1. So that's correct. And the second eigenvector is sigma x prime is equal to minus 1. That's equal to a thing. 1/2. Check it in a minute. 1 minus 1. So if it is minus 1, 0, minus 1. Oh. 1 minus 1, but then write this as minus of 1 minus 1, and that's so that's your eigen vectors. Now that should be straightforward, and again, if we were to write this, one way to say this will be sigma x in the eigen in the eigen, so maybe sigma x. This is maybe description, right? Sigma x in the eigenbasis of sigma z. Right? That's given to you in the beginning when I gave you that structure. That's what it was. One thing is very clear: sigma x in the eigenbasis of sigma z, no, sigma x itself would be equal to, we know, sigma x would be equal to 1, 0, 0, minus 1 again, and this will be equal to sigma x is sigma x prime equal to plus 1, sigma x prime equal to plus 1. Minus of sigma x prime equal to minus 1. That should be straightforward. You can almost see Niranjan. I just went a few centimeters. Okay.
Oh, thanks.
Yeah. Okay. That's sigma x. But now we can always say, what is sigma z in the eigenbasis of sigma x? And that's what quantum mechanics deals with. Suppose I make a measurement, and who decides which eigenbasis to decide? That's the measurement. Whenever, so suppose you're measuring momentum, if you're not in the momentum basis, if you're on the position basis, that's a different basis here. So you have to make sure that measurement decides the which basis to choose, and already whatever the system is in, that is a previous measurement decides which system the state is in.
Yeah, sigma x in the base, that's sigma x.
Yes. Sigma x in the eigenbasis sigma x will be diagonal. Right? Usually this is sigma z. But sigma x in the eigenbasis of sigma x, that's a trivial one. That will always be diagonal. Right? Is that clear? Like this is not a mistake. Like usually this is sigma z. In the eigenbasis of sigma x, it is diagonal. Now I'm saying, what is sigma z in the eigenbasis of sigma x? Usually we work in sigma z eigenbasis. Like this is what will happen if you were to measure sigma z first and then measure sigma x. First, you have a magnetic field in the direction of z, and then I put the magnetic field in the direction of x. Then whatever I'm going to get is going to be the result. Like what is the probability going to be? That's going to be decided by the matrix elements of this structure. Okay, that's what quantum mechanics is. But for us, this is just an algebra. So what is it? So let's first deal with Ij, right? Components. Right? That's the components of the matrix, and this one is we are in the basis of sigma x, right? So this is sigma x prime equal to +1. This is sigma z. Sigma x prime is equal to +1. Sigma x prime is equal to -1. That's a matrix. Sigma z, sigma x prime is equal to +1. That's a matrix multiplication. And this is sigma x prime is equal to +1. Sigma z, sigma x prime is equal to -1. And the same thing. Okay. Unlike earlier, we cannot do this in our head. Earlier, it was an eigenvalue equation, so we immediately did this. But now I had to do this multiplication in my manually. So sigma x equal to +1 is this 1/√2. 1/√2. This is a row, so I have, if this was complex by any chance, I have a complex conjugate. Don't forget a complex conjugate. It turns out that I'm working with all real, but whenever there is a sigma y, that's a complex conjugation. So don't forget the complex conjugate. So this is 1, 1, and this is 1, 0, 0, -1, and this is 1, -1, and that is 1/√2. That's the first element. The second element is 1/√2. -1, so this is 1, -1, 1, 0, 0, 1. This is +1. Oh, I messed up, right? This is plus. I had messed up here. This is plus. 1/2.
1, 0, 0, 1, 0.
Yeah, the answer is in?
No, the matrix.
Oh, this one. Thank you. Yeah. Yeah, correct me. And this one is 1/√2, 1, 1, 1, 0, 0, -1. And this is -1, -1, 1/2. And again, 1/2, 1, -1, 1, 0, 0, -1, 1, -1, 1/2. Okay. So this is equal to, there's a 1/2 for sure, and then there is 1, 1, there's 1 and 0. This is 1. This is -1. So 1, -1, that's 0. That's 0. First element is 0. Second one is 1. All right. Sure, 1. Now I. Yeah, there's no I, right? Yeah, sure, okay, that's 1. Then this also could be 1, I guess. Oh, let's 1. That's 1. -1. 1, 2, right? 2 divided by 2, that's 1. That's -1. Which is in the old basis, let me not write it because it's confusing. This is sigma z, notice. But this is in the eigen basis of sigma x, and it is actually sigma x in the eigenbasis of sigma z. If you were to have 4 minutes, let me do this. These are the matrices. It is good to write it as an operator, right? Sigma z in the eigenbasis in sigma x, eigenbasis of sigma x, right? That means, right? Better notation would be good. This is equal to sigma x prime equal to +1, sigma x prime equal to -1, 0, 1.
Sideways.
Oh yeah, oh both.
Can you move the camera, please?
Yeah, almost, yeah. Okay. Thanks for asking. Sigma x prime is equal to +1 output. Sigma x prime is equal to -1. In the outer product, so sigma x prime is equal to +1. Sigma x prime is equal to -1. And now our outer product formula 0 times this. And this is sigma x prime is equal to -1, comma. Sigma x prime is equal to +1. That's equal to, notice how things are coming, this times this is a different values. So sigma x prime is equal to +1 is now going with sigma x prime is equal to -1 plus sigma x prime is equal to -1 +1. If I were to write it, write sigma z eigenvectors were E, right? E, EI, let's say, and sigma x eigenvectors were GI. If I were to think of it like that, then sigma z is equal to sigma z in sigma x, right? And the eigenbasis of sigma x is sigma x is +1, so this is the basis now. This is G1, right? And this is G2. Notice how 1 and 2 are coming together. This one is G2, G1. Right? That's how you build more operators. So in quantum mechanics, one of the things that you deal with is that given a space, for example, this is a two-dimensional space, how many independent operators can you build? Notice we are not talking about how many independent eigenvectors you can build. Now I have a space, I have a two-dimensional space. You can ask how many independent operators can I build? Independent. And it turns out in this case, there are 4. So there's a sigma x, sigma y, sigma z, and the 1. And why that is 4, you will see that in the homework. Okay? At least a motivation for it. It won't be a proof, but you will construct those 4 pieces in the homework. So that should give you an idea. So if it's a bigger space, how do you go about which operators should we deal with? Like, is it always fixed, or is there a fixed number of operators that you can always build? And these are, so once you have the number of operators, that decides the degree of freedom. Right? For example, if I can measure position, momentum, energy, time, how many operators can I decide on? In quantum mechanics, apparently, it's fixed. And these are called quantum degrees of freedom. Like, given, if you start with a space, you're decided with how many operators you can build on. And I'll stop here. 1.5 minutes. And in your exam, there will surely be a question of find the matrix representation of an operator in the eigenbasis of something else. Like whatever is your homework, the last part of the homework, I will just change x or y. In your homework, it is x in the basis of z. Then I'll ask you z in the basis of x. And that should be, you should be able to score that easy. Okay? I just make sure you understand it. And I'm not asking this, this is the basic thing about quantum mechanics, like at least the working principle of, like the ideas are different. But this is the, what do you call it? Mechanical part of the quantum mechanics. Okay, thank you. Nice, next class. Thank you.
Thank you, Dr. Sajas. See you
Yeah.
next time.
Yeah, this has matrix, the same as the.
Yeah, this is the same as this one. Yeah. It's just that these are the components of the matrix. This is the actual matrix. This is the operator. So this is an abstract thing in the sense that using eigenvectors, I know the matrix. Now I can use this to operate. This is only the components of it.
For the question is on.
This one. I'm asking the representation of sigma z in that. So that's this is, I don't, in this course, we won't use this, but in quantum mechanics, especially quantum information uses it a lot. So, and there the notations are different, that's all. But here I'm putting in all the details so that you know what's in. So then I'm not right. Okay.